in general, like the history of the short history of the architectures in deep learning. So up until recently is like 3 years ago, or yeah, about 3 years ago. Uh, like there were three main architectures: the CNNs, which are the convolutional neural networks. They were used a lot for vision. So as you see, it kind of is able to handle images properly by iterating over patches of images. You also had the recurrent neural networks, which were designed to handle sequences, and you had the here it's called dense, but it's also like the perceptron, which is basically every neuron is connected with every other neuron, and use it for like arbitrary problems. So like the use cases, they were each specialized. So like CNNs were good for vision, RNNs were mainly used for text and also audio. CNNs are also used for audio, so they share kind of a domain. And then you have dense, which you can use it for like I don't know, analyzing tabular data or things like that. And that was kind of the landscape. And very recently, like deep learning got a big shift. So the thing that happened is that the the attention layer, also known today as the transformer, um, started getting like really good results initially in NLP in text, and then it started expanding. So the real interesting stuff is that it seems that attention, like the same mechanism, is able to do like many domains. So like text, vision, audio, but also things things as complex as graphs and point clouds that the previous methods can't handle. So it seems to be very general, and that's very interesting for a method. So it's getting a lot of, no pun intended, attention recently by the research community. So okay, for the ones who already know about the topic, this is going to be like like a very like basic introduction. But if you don't know, then this is where you can get the intuitions. So okay, we're gonna talk about like what is attention in general. Like if you use techniques to inspect what a model is doing, you can see that it sort of has the notion of attention. Like if you try to uh, like based on a certain classification, and you try to see like why the neuron got activated, you see that it kind of got activated because it's paying attention to certain pixels. So in the image at the bottom, like you see that the classification for cat mostly focuses on the pixels on top of the cat, not all of them. And the neuron for the dog focuses on the like mostly the face of the dog. And you can think of this as implicit attention. It's implicit because it's kind of deduced. It's not like coded into the architecture. So we're not going to talk about this. We're going to talk about explicit attention. And in explicit attention, like the model has like the architecture uses what you call an attention mechanism to model attention explicitly. So yeah, the attention is like coded into the model, you, so to speak. And you could see it in two ways. For example, one way of looking at it is if you're kind of looking at an image, your like your eyes kind of jump all over. So if you look, for example, at an ear, you could jump to or pay attention to some nearby region. So if I'm looking at an ear, I might want to pay attention to, for example, the eyes or the nose to deduce that this might be a dog. So attention is kind of looking at specific regions based on maybe other regions. In text is much clearer. Like if you're like, and humans do this a lot. Well, in the like scanning the image with the eyes is also like a form of attention. But for example, if you read the phrase like she's eating and you don't want to read everything, you kind of maybe want to know like what she's eating. Like so based on that, like you can try to quickly search for the source of what it's being eaten. So you might jump to directly to Apple. So you could see as if you're like eating is paying attention to Apple, and Apple. If you look at Apple, you might want to know like what Apple. So you can pay attention to green. So you see, it kind of creates like a graph. Um, okay, so that was like the intuition. So this is we're going to start very basic into like a definition of attention, and this is uh, very intuitive. So if we wanted to model, we can model attention like as having a collection of elements, which in this case is going to be this at the top, and we could see like when we're paying attention, we kind of always have like a query, something that tells us what we should try to pay attention to. So in this case, it's going to be like a tire. And if we wanted to say something like, okay, which object has a tire, um, we could like mathematically model it, basically having like the answer should have like a 1 and the other items should have a 0, this kind of a score. And if we do this simple operation, we kind of selected the car. Uh, so how do we do that? Well, we multiply and sum, and basically all the others are getting canceled, and we get the car. So that's how, like, mathematically we could model something like attention. The thing is that here we use like ones and zeros, which we can't in neural networks because they have to be continuous. So what you can do is you could like make this like a distribution where the like probability is concentrated at the car. So we just do it like this, and that kind of fixes the problem. The only thing is that we now get like a car, but we also get like a little bit of the other like elements. So it's mostly a car, and well, that kind of works even if it's not perfect. Uh, so just some notes. Attention, you can view it as a form of pooling. Like we have like a bunch of objects, and we basically get one out. So it's kind of pooling, and it's similar to like a soft indexing. Uh, so some conventions, we are going to say that the objects are going to be like the keys. So we have kind of three, like, let's call it sets. We have the keys, the queries, and the values. So in our example, the keys and the values were kind of the same and were the set of objects, and the query was the tire. So this is very standard notation in the attention literature. So we can view attention like as a function. So if you take the query and a key, it gives you the amount of attention you should pay to that object based on the query. So these are basically just the numbers we defined previously, but well, we're getting a little bit more formal. Um, so to put it all together, you could define like an attention layer where basically if you get a query, a key, and a value, you compute the attention as we described in a previous slide between the query and a key, and you multiply it by the value. And doing this is basically the like linear algebra uh, notation for just doing this, which we did very simply in pictures. So it's just just like multiplying and adding. So like if you haven't seen this, it's just the same. Going to skip this in interest of time, but you can have multiple queries. Um, okay, so this is where we go a little bit more to the math. So basically, when you do have attention, you do it well with vectors. So each of our objects is a vector, and so we have to learn, right? So what we do uh, what we do to learn like a model is like we get a set of weights, one per for the query, one for the key, and one for the value, and we basically just do the dot product, and what we're going to get is kind of a new query, a new key, and a new value. They're just kind of like shifted by these weights, but uh, they're going to be like the same for the operation of attention. We will see later, but these weights basically do the learning, so they're kind of the important stuff. Um, but the math is basically what we uh, talked about previously. So to actually formalize the attention, instead of a table that I give you, we will give it a form, and it's basically going to be the softmax of. So I'm going to explain this, but I'll just say right now it's the softmax of the queries times the keys. So let's just see what this means. Because if you haven't seen this, then it's very arbitrary. So it happens that if you have your queries and you have your keys, you're going to pay attention to the things that are most similar in at least in a vector space. So the thing is that like if you multiply two vectors, that is proportional to what we call the cosine similarity. So we can actually visualize this. So if we have two vectors for two queries, let's say the hand and the tire, and we have these objects which are the keys. So initially this is random, right? But we ideally would like the hand to be near the person and the tire to be near the car. So basically we want the angle between them to be close to zero. Uh, and if that happens, so how can we achieve this? Well, we have learned weights. So basically we hope that the network learns that they should be close. And if that happens, so this is a possible configuration. We get that the tire is near the car, the person is near the hand, and maybe the dog and the cat should be near, if that helps. And basically, what we get is that those vectors match, so they're kind of large, and the softmax will kind of select the answer as we showed at the beginning. So it will give a large number for the associated key, and we could get a table like this as output of the attention matrix. So we get that I don't know, the tire pays a lot of attention to the car, and the hand pays a lot of attention to the person. So okay, I did a bunch of cartoons, but this works for translation, for example. Like if you're trying to do like an understanding a phrase, uh, like the animal didn't cross the street because it was too tired. this is kind of a canonical tricky phrase because it is ambiguous. So the network, if it's doing like a proper understanding job, should know that it could mean the street or it could mean the animal. And for this case, like for us humans, well, we understand it, but like for the machine, it should figure out that it's mostly talking about the animal, and maybe it's the animal because the animal gets tired. So it should pay attention to tired and to the animal. And we see that it does. So it pays attention to this, and maybe that helps it like understand the phrase. So in for example in translation, this is kind of an attention matrix you can get. This is translating between French and English, and there is kind of a well-known thing where the words in at certain positions are in different order, uh, and you can see that the attention matrix shows this where it says European Economic Area. Uh, so that's kind of good to know what the model is doing. And finally, we have the attention layer, which is basically the softmax, which is the attention. And then, well, we already did this in the picture. So if we already have the attention, we should actually extract the value. So we extract the value by multiplying the attention by the values, and that's kind of a soft indexing we talked about. And that this is the whole attention layer operation, um, which turns out to be just matrix multiplication with a softmax, but it has a lot of impact. So we can also try to understand attention, like the attention layer, like as a information routing. And I'm going to give an example. So this is what we had previously, and you see that I draw the arrows, so they're kind of the vectors, and we basically want the vectors to line up. So the hand is like closely the angle related to the human, and the car to the tire. So you end up with like a graph like this. This is kind of the graph of the attention, and you can understand it as like the the information from the car being routed to the through the tire to the next layer. Um, like if you have more layers, then like you could imagine this like processing information based on like I don't know, similarity or whatever the network decides it's useful, but it's kind of, yeah, it's routing information between the like the items. In this case, it's the queries to the values. Uh, but okay, one thing that's important is that if you look at the dimensions, you can see that this inner matrix is n by m, and like the whole operation is n by d. But it happens that usually like n and m are the same because that's what you use. It's something called self attention, where like the inputs, like the queries and the keys are the same. So you get an n by n memory requirement, and that is really bad. I'll talk about some like things that are being explored to try to solve this, but like the attention layer is very heavy, uh, and it's a restriction because every time you have n squared memory, it's like you're limited into how many elements you can process, and this gets worse because you usually have something called multi-head attention, which is that you just do like the attention we described h times, uh, So an H is usually something like 12, so it's like significant. So you have the previous by 12, and you have additional weights. So you basically concatenate the output of the, in this case, 8 heads, uh, and you concatenate them and you multiply them by an additional weight, uh, which is for the output, and that gets you back to like the dimensions of a single head, but you have even more computation. Um, I'll talk about some applications very quick, and then maybe we can get to the questions, which might be more interesting because it's a hot topic. So basically, the application that got attention really popular is NLP. So they started with translation, and in like a year or so, it basically consumed the whole NLP field. So it started with the attention is all you need paper, and then BERT, GPT-2. Now we have GPT-3, Albert, and you have a bunch of new architectures. Um, and historically, you can see that like like a little bit before BERT, like the field was kind of like plateauing a little bit, and then you can see the jump before BERT, and then you have like a new boom in accuracy for this squad 2 like challenge. Um, we also have a graph attention network, so like the attention mechanism is so general that you can also like do graphs. Um, so that is something that got very high performance in things related to like classifying like molecules and a bunch of other stuff, but it worked really well on that one. Uh, so very recently, I had to update the presentation for this. We have like transformers in for images. So what you do is that you break the images into patches, and each patch then becomes like basically like a word or a word or just like an element, and then you do the whole attention processing, and that works really well. Um, it works. Going to put a star. It works really, really well if you have a bunch of images. So if you have like millions to billions of images, it beats CNNs. Else, like you could still for like small amounts of data still use a CNN, and it's better than the transformer, but in the big data regime this seems to be very powerful. Recently, like this was a boom, like DALI came out, and DALI is a text to image, so it uses like a transformer to generate like generate images based on some text. So it's amazing. Like if you get a prompt like an illustration of a baby daikon radish in a tutu walking a dog, you basically get an image representing that, and this is amazing. Just to show a little bit more, like like you get an armchair in the shape of an avocado, and it produces very different but very like good representation of the prompt of the text. This is my favorite. Like a snail made of harp, a snail with the texture of a harp. And this is just very crazy. Like, I don't know. It's like, it gets the textures, it's very artistic, so it's impressive. And you can play around with it. If you search for the DALI blog from OpenAI, and there's a bunch of examples. And lastly, but not least, it's GPT-3. So This is like, I don't know, like GP3 is so famous that I mean you get a bunch of articles daily about what GPT-3 can do. Basically, they took these models to the very very like big like data and big model regime. So they train a 175 billion parameter model, and it turned out to be so powerful that it could do few shot tasks. So you just gave it a prompt, and you gave it examples, like in a way that you tricked it to do like a task, like you give it a phrase and then I don't know, colon and the answer, and then another phrase, colon and the answer, and then you could sort of trick it into completing. So this for language modeling, it knows how to complete the next word, but you can trick it into doing some patterns, and it turned out that you could do what is called few shot tasks, and few shot tasks are very useful for the industry. You could basically, without training, you could get the model to do like real classification tasks for you. So it's very powerful. And I already mentioned this one. And yeah, I think this is it. If I can share the link, and this is like a lot of the references I used, and I'll take questions. Um, and thanks. Okay. Uh, Let me see. What are the differences between additive and multiplicative attention? Okay. Vikram is doing like a trick question. There's like a lot of attention, ways to model attention. Uh, so like what I showed you, it's called dot product attention because it's the dot product between the like the queries and the keys. You do a dot product and then you do a softmax. But there are many mechanisms. What Vikram is talking about was like a previous mechanism that was used. Like the formulas are slightly different. I think additive uses like a tan h, and the equation is slightly different. But like there's like a whole literature into like ways of modeling attention. It just happens that dot product attention is the one that is mostly used today. So like you will find it in recent papers, but there are many ways of doing this. uh, let's see more questions. uh, Natural language processing, not familiar. Okay, this is not a question. Okay, it seems that was kind of the only question. um, I don't know, Vikram, do you want to say some words?
Sorry, I'm on mute. Thank you, Christian. This has been great. And I'm going to invite a few people on the stage, maybe to just have a chat, if not a question. If you have a comment to make or a discussion, I just invited Hisham. Hisham is here. There's a raise hand feature on the right hand side. So if you click on that, I can bring you on the stage. So yeah, feel free to comment or share more inputs. I think we have Sikandar.
Okay, there's a question, I think.
I was going to ask the question live.
Oh, for sure.
I I actually still struggle with attention up to now because I worked a lot on LSTMs, and then attention came about, and they were like the new. They replaced LSTMs in this field, But after, I don't know, 2 years of looking at attention, I still haven't figured out how attention and transformers handle the variable length. That was the whole reason for LSTMs, that they could handle variable length inputs, which the original neural networks couldn't. So how do transformers and attention do that?
That is a good question. Let me see if I can Google like a diagram of the transformer decoder. Is called transformer decoder. Um, okay, so there's two things. Like without going into the decoder, which is a bit different, but uh, like if you look at the equations I showed, or the let's just go to the simple like drawings. Let's go. Let's go maybe here. If if you look at what we're doing, we're basically just assigning like a set of objects, and it could be like any set of any dimensions. We're assigning like a value per object, and that is the attention. Uh, so the thing about the attention mechanism is that it doesn't care about the input size. So that's very nice. Why doesn't it care about the input size? Because, well, now sadly you have to look at the math, but basically if you have like let's imagine I can't edit it. Just gonna maybe I'm just going to put it down here. The reason is because if you have a Q as an input and you have Q transpose, because well, this is for the case of self attention, which is the most common. Like Q times Q transpose will always like you can always do it. So um, that gives you like an attention matrix of n by n, and what that results in is that like what matters are like what elements the queries are attending to, but it doesn't the number of elements doesn't matter. So like more generally, attention doesn't not only it doesn't care about the length of the input, it also doesn't care about the order of the input. So that is very important. Like if you see all these, I mean, you could go a little bit more into the what's happening exactly, but uh, you might notice that yeah, it doesn't matter. Like if I move the car uh, from one place to the other, it will still put the same attention to it because they just share like the same cosine distance, let's call it, regardless of the position, and the softmax doesn't care about like where the element is. So that yeah, that is one important property like of attention. And yeah, I don't know, by virtue of not caring about this, it can handle like multiple length, but it can also like handle arbitrary sets. So that's why it can handle graphs, like sequences. Um, there's tricks to handle text, which I didn't mention, but you have to trick it into knowing it's a sequence. I don't know. I hope that helps. I just gave a lot of information, but the mechanism is so general that like it can do a bunch of stuff that previous method did, plus a bit more, and it's very interesting, in my opinion.
Thanks.
Okay. Any other question? Google has a feature to recognize images for search prompt.
Hello, sorry, I came in a little bit late, but I've seen some of your slides and all this. it's interesting. I have like a, I don't know if you talked about it earlier, but how do you create that specific attention to an object? Do you push like an intentional bias, or does it create that attention by itself? If giving like let's say variables, like if the thing is moving, like if the car is moving, then concentrate on the car, or does it understand that if something is interesting in on the stage, then I'll focus on it? Like, is it intentional bias, or like kind of like self-aware of what's going on? I still don't.
Okay, yeah. I think the slide that helps you is like if you have these elements which I use throughout the presentation, like if they're going to pay attention, like you're going to do, you want their vector representation to be similar.
Mhm.
So in this case, something like this would work, like the vector representation of the tire close to the car and the hand close to the person. And if you do the dot product, which is the equation we're using, like their dot product is high if they're pointing like in the same general direction. And if you pass the softmax on top of that, then you get like a high attention based on like this simple linear algebra. That's kind of how it works. So basically, just make the vectors similar, and then you're just doing things by similarity. Obviously, you have to learn, like, because I mean things are not similar just because they are. You have to learn like this. You do some transformations with these weights, and the weights should hopefully like turn the vectors in directions such that they point in directions that are convenient for the network. That's kind of the idea.
Okay, so it realizes by itself, like it mimics a human behavior, that to pay and to or to focus on things when they are related to each other, like the human eye or the human brain. Like if you look at a person, you just see them all, like where, or you focus on the facial expressions, or the hand gestures or something like that. So you just choose which like, are you focusing on the face? Are you focusing more on the? It's like simulating a human behavior when it gets the focus, right?
That's kind of the idea. Although it's doing like a bunch of attentions in parallel, so basically each query is like something that pays attention to other stuff. Like if you're only doing like more like a human thing that humans kind of pay attention to, like mostly one thing,
Mhm.
would be like attention with only one query, like I don't know, an image and what is like, I don't know, some the most interesting thing, then it's going to be like a query of what is interesting, and then like a procedure that somewhat that I describe, which tries to see like which matches the best, and that's what how you get the attention.
Okay. One thing before we go to the next question. Have you do you work, or have you considered cognitive functions, for that matter?
Sorry, cog what? Cog,
Cognitive functions.
cognitive?
Yeah. Like.
I haven't seen
Oh,
them.
okay. I was just asking the question. Okay.
Okay, yeah.
Thank you very much. I think Mike have something to ask. Mike.
I think this camera or speaker issues there.
Yeah, I think something is loading up there.
Yeah.
Yeah, I think Mike is muted, but yeah, he couldn't speak.
Yeah, I can see his message. He says, but you can text Mike. You can text your question if you cannot speak.
Okay. So I'll ask one question. So generally, our group is all about biases and understanding, how this gets in the way. And I think part of that question Hisham also asked earlier. So how can we be more aware that at a basic foundational level, how to avoid or what kind of questions to ask to make sure that this is not targeting or introducing some specific bias, racial or otherwise. What are some of the ways to counter or balance that? Is it just somebody programming it needs to pay attention, or what are some of the ways?
Oh wow, that's a very tough question. It's very tough because it's an ongoing research, right? So there's kind of no answer that like you could effectively use right away, like as a like if you're going to deploy something and you want to try to like see what kind of biases your network can have. There is no easy way of knowing apart from just doing some test cases and basically yeah doing a lot of testing by like the people in charge that they want certain behaviors to hold. So the problem is that like these models, like most of the models I showed you, they're trained on data sets that are they're huge and they're so big that it doesn't make sense for humans to go through them like one by one. So like I don't know, GPT-3 didn't even like release its data set, but it's a data set that is basically like I don't know half of the web, something like that. Is the scale is absurd, and some other recent like networks from other groups they're trained on basically yeah I don't know some are private but they're very big, so these are on the I don't know like very like big data regime, and that is like troublesome because usually a way you can try to make these models like I don't know like strip certain biases out of them is basically curating the data set,
I,
but that is not a possibility for some data sets.
if I can
So
weigh in on that, um,
oh
just
for sure.
I I um I have a different take on that. So, and I'll give an example more so than a technical explanation. I used to work mainly with LSTMs for demand forecasting. So the business use case is you're using a neural network, a specific type called LSTM, to forecast demand for a retailer to figure out how much you should ship to each retailer every week based on historical sales patterns. Now, the pitfall there was that the LSTMs had very accurate predictive power in terms of predicting demand, but they were really hard to understand what they were doing. Now, what would happen is you would use zip code as an input to the LSTM, and then you'd find out a few months later that because of that, it was inferring the ethnicity of the demographic around the store from the zip code inadvertently and shipping lower quality products to a neighborhood because that particular neighborhood had a lower income level and therefore was much more likely an historically underrepresented minority or something like that. And when we switched over from LSTMs to attention-based models, transformers for forecasting, attention is what allowed us to explain why the deep learning model was forecasting. So it wasn't the problem. Attention was the solution to the bias problem, because now we could go back and see why the neural network was generating the predictions. And then if we got notified, but okay, wait, we have to stop including zip code as a feature in this model.
Hmm. Okay, yeah, that's very nice. So what Scanner is talking about is so one nice thing about Transformer, although I mean this is not like universally done, but um, what you can do is you can look at the attention matrix, and here's just one example, and you could actually see okay, like what is it paying attention to, right? So this is because the model like molds the attention, then you can use it to debug. So I don't know, here's just translation, but you could do something like okay, which feature is it paying attention to, and if it's paying too much attention then it's important. and the model tells you, hey, I'm looking at this. So it's kind of a way of debugging what the model is doing. I'm happy to hear that it worked because, like, I mean, like, for certain cherry picked cases, like the authors show it, but there's also some, I don't know, papers that show that the model is doing things that they're not like very like readily understandable for us humans. But like, if if maybe you can like do a lot of visualizations of these attention layers, you might get like an intuition into what it's doing. So that's kind of the workings. And yeah, so yeah, attention is a little bit debuggable, but you have to do work because yeah, it's not free, and sometimes it's hard to understand, but you can try to do it. Uh, but I also have an opinion about the general case. So like, if you have like certain type of variables that you can understand, or are like, um, I don't know, less I don't know I don't know talking about text, for example. Text is hard because you don't always have the same features, and you could get like very different combinations of words, and that's just like a huge universe, which is very hard to understand the distribution of your data if you have something like text. Like, I don't know, if you have something like a tabular data, or yeah, so something like a database, you kind of can see certain patterns of your distribution. But if you have text or images, I mean, pixels and combinations of words can be anything. So it becomes very hard to understand if your data is biased somehow. Uh, and and that, like, to see if it's biased, you have to input it to look at the attention, maybe. But you still have to find the correct inputs that would yield like negative cases. So that is still a problem. Like, well, you can do techniques to try to solve it. There's still the problem of um, finding the inputs which are like, which have problems of a certain bias or something like that. So so yeah, there's like these two things that like you can try to solve it, but it's still not solved in general. Is there another question?
Yeah, we have two questions in the questions tab. So one is from Mike. He was not able to ask it on camera, but the question is, was wondering how well Transformer handles perturbed patterns. Example, given an image with lots of noise, how well does it do it?
I mean, that's kind of a trick question. So my short answer is, I think if you give them enough data, they're just as good as CNNs. So that's what the literature has shown. Like, um, so I mean, if you perturb the images in ways that uh, make sense, the attention will just work with it. So yeah, I mean, it's as good as a CNN. So if you keep that in mind, then like, you're good to go.
Great. I think there's one more question. But Gen, you're here. Do you want to ask the question live?
Oh yeah, I'm just messed up, so I missed the first hour of the things. But yeah, Cristian, I read your bio a little bit. You said you work on the autonomous driving, the AI part, neural network, and also you mentioned that this attention, the new approach can help the vision. So I just wonder, if this approach will help the vision problem, in autonomous driving, particularly whether they will help to create a pseudo LiDAR system that just use vision system like cameras instead of LiDAR to get the 3D, distant detection capability. Thank you.
Okay, so there. I mean, like if you're using images, then it's okay. It's the same as a CNN. Maybe better if you feed enough data. It might be better than the CNN in the big data. Big data, no, very big data regime. But there's also this like architecture called the SE3 transform, which let's see if they have some images. I don't know if they have the correct images. One that is intuitive. Okay, so since transformers are so general, they can basically also operate in more geometric like objects, like for example point clouds. So that's kind of what you do if you have a laser. You have like a point cloud representation of the world, and transformers and other things called graph neural networks. They're very good at this kind of data. So because this kind of data is like a set, and it's not ordered, but it has certain like geometric properties. And one example of a transformer which is good at that is called the SE3 transformer. I don't know, you could check it out, but it has this notion of it tries to incorporate the notion of like rotational 3D rotational invariance. It's a bit technical. I haven't finished the whole paper. It's not easy, but the end result is that transformers can also do like this kind of things that are good for like 3D data. So that is very interesting because it's kind of a data regime which is not easily solved by like basically CNNs, LSTMs. They all fail at that. You have to use like graph neural networks or transformers. And yeah, if you have later, you might leverage some of these technologies, and the transformer is one that is able to do this. So yeah, maybe a partial answer, but you can look into the like this kind of stuff.
Awesome. All right, good question. Any other questions? Maybe one more. Skandar is requesting to share the link for the paper. Cristian, if you can post it in the chat, that will be great. Yeah. Thank you. There is a question. Let's see. No, I think we answered everything. Thank you so much, Cristian. This was awesome. We will go back to the networking lounge and maybe hang out a little bit more, but we can end the live streaming session. Thank you so much. It was not an easy topic to talk about. We all know that. And you did a wonderful job in explaining, both people who had the background and people who didn't. So this was fantastic. Thank you.
Okay, Vikram, thanks a lot for the invite. It was very fun, and bye to everyone.
Yeah, let's meet at the lounge and continue a little bit of networking session. If you need to go, totally understand. St. Patrick's Day. Happy St. Patrick's Day, everyone, and see you in the lounge.